So I am Amy McGovern. I'm going to talk about he said, the need for trustworthy AI for weather to facilitate sustainability in our changing climate. But I'm going to start by talking, about our NSF AI Center, as he mentioned. And the motivation for why we wanted to create this AI Center for weather, climate, and coastal oceanography, there are a bunch of motivations, and so I have a couple of slides on them, and we want to address all of them. The first is that we want to improve our resiliency to climate. So things like this picture show what happens when a tornado goes through the southeast. When hail hits a house, that's my hand holding hail. You know, we've got hurricanes that come in. We can't stop any of that weather. And as the climate is changing, we're getting more and more effects of the severe weather. But if we can improve our predictions of it, then we can help mitigate the effects. This is a picture from pre-COVID times. They just started to resume the sea turtle releases, but this is a picture from releasing some sea turtles back into the sea after a cold stunning event. And that's another application area that we work on. And then we also have coastal oceanography as part of our name. So trying to improve our understanding of a wide variety of coastal phenomena. And here they're releasing some probes into the ocean. So if the climate resiliency just pictures isn't enough, the second motivation would be to look at the billion-dollar disasters. And so these are the billion-dollar disasters that have happened just this year. So this is only through June of 2021. I used to have the 2020 picture up when I gave the talk, but figured I'd move to the new year because the new year is continuing to have disasters. We have a fire that's not even shown on here that's been burning for weeks and weeks. That's not yet under control. We have a hailstorm that destroyed a number of houses and including my own. I'm on roof number 4 now in Oklahoma in 17 years. All of these events, again, can't be controlled, but if we can use AI to improve their prediction, we can do better at improving resiliency. The third motivation to look at all of this is that if you believe that we can use the AI to do the predictions, another motivation to think about is that we have a huge amount of data overload. There's new sensing systems that are coming online all the time. We have new satellites. Some of these satellites are providing data at a 30-second interval, for example, a minute interval, high resolution data. There's so much data that it's being thrown away. The studies that we hear from NOAA are that they're only using less than 3% of the data that are coming down. And that's 3% live being ingested into the weather models. And if you can imagine, you could just use 10% of it, you could improve the weather models and the weather predictions. We've got mobile radar, we've got crowdsourced data, and we've got a lot more. So sifting through all this data in real time is ignored, and we really want to be able to use AI to be able to improve this. And then looking at the as we get to the nature of the fact that we're trying to make trustworthy AI, the forecasters need to make life or death decisions. Are they issuing a tornado warning? Are they evacuating for a hurricane? Are they the end users' needs really matter, and the AI that we're creating is focused on making trustworthy AI for different end users. The end users are making these life or death decisions. The end users are making critical protective decisions. So if it's not a forecaster, it might be an emergency manager. It might be the general public. All of their needs matter, and all of their needs are slightly different. Do you close your business early? Do you send everybody home? Do you get on the roads, or do you go into your shelter, for example? I see that there's a bunch of questions showing up in chat. I'm assuming that this is a...
Yemi, yeah, this is a Zoom distance. Yeah, you can continue.
Okay, are you, we're good on the side? Okay, then I will continue. Okay, so all of these things together bring us to what we're doing at our NSF AI Institute. So we are the NSF AI Institute for Research on Trustworthy AI and Weather, Climate, and Coastal Oceanography. We are led at the University of Oklahoma. I'm the director of the center. We have 8 universities involved now. We have Texas A&M, Corpus Christi, North Carolina State, Colorado State, University of Albany, University of Washington. Del Mar College is a community college. They work on our community college outreach, which I'll talk about. We have a brand new partner, Central Michigan University, just signed on this week. And then we work with the National Center for Atmospheric Research and NOAA, as well as a variety of private industry partners. So our founding private industry partners include Google and IBM, Disaster Tech, and NVIDIA. And we have since added Park, Vaisala, and Radiant Earth. And together, all of us are working on the mission statement that we have over here, which is that we will uniquely benefit humanity by developing novel, physically based AI techniques that are demonstrated to be trustworthy. And so we'll talk about what that means. And will directly improve the prediction, understanding, and communication of high impact environmental hazards. So this is a picture of our team. The full team is huge. And so what we did in order to make the team visible and so that you could actually just read the names and perhaps find names on there that you knew somebody of, and you could go talk to them. Was we put everybody with PhDs and above on this list, and that'll tell you how large our list is, because there's a whole bunch of students that aren't even on this graphic yet. The people whose pictures are at the top are all the leaders of the different areas. So if you get excited about one of these areas, you're interested in working with us, any of the people whose pictures at the top are happy to talk to you. So I'm just going to give a brief overview. Our focus, our 4 foci that we have, the first 3 are intertwined. Those are our research areas. So we're focusing on foundational research in trustworthy AI and machine learning, use-inspired research on trustworthy on environmental science, and I'll talk about the different areas, and then the foundational research in risk communication. And then I have one slide to also talk about our workforce development and broadening participation plans. So briefly looking at what we're doing to create the trustworthy AI and machine learning, we have 3 main goals. We are working on developing explainable AI methods that are aligned with environmental science domain perspectives and priorities. And what this means is we're not just looking at XAI from the typical perspective, which is often just sort of image-based things like ImageNet and all of those networks. We're looking at developing methods that focus on the needs of the environmental scientists and users. So the regression-based problems, the fact that almost all the data is spatially temporal autocorrelated. We're looking at developing physically based AI techniques. And that includes, what I mean by that, by the way, is that we are respecting laws of physics and we're incorporating laws of physics directly into the AI techniques. And then finally, developing robust AI techniques to ensure that they are both robust empirically and theoretically, with adversarial data. And we'll actually talk about that a little bit later when I get to the ethics and responsible AI aspect. So I said that we have a specific set of research problems we're looking at in environmental science. We have 5 domains that we're working on. The goals in here are that we want to use trustworthy AI to provide actionable information to a diverse set of environmental science users and to enhance both scientific and physical understanding of the processes. So we want to be able to provide improved predictions and also to improve our understanding. The 5 domain areas, the first one is convective weather. I just have a quick graphic here. Convective, if you're not in the weather domain, means anything that has to do with basically with the thunderstorm. So severe weather, this includes tornado, wind, hail, lightning, other severe weather events. The picture here is just showing the inside of a model. We're looking at what we had learned inside a model. It was predicting tornadoes. Our second domain is winter weather. So winter weather impacts the United States broadly. We're studying it in 2 locations. We're studying it in Albany and in New York and in Oklahoma, where we have 2 very different sets of winter weather. And so it gives us a more general answer. They get a lot more snow, we get a lot more ice. Both of those are impactful events. The third application area that we're looking at for environmental cyclones is for environmental science is tropical cyclones. Here we're trying to improve our understanding of tropical cyclones in general, but specifically in this picture, looking at the rapid intensification of tropical cyclones. And the example that we show here is using AI from one type of satellite that's available every 10 to 15 minutes to mimic the data that's available only several times a day, and to ensure that the AI we develop is trustworthy, so we can then use those created images to better understand the tropical cyclones. The fourth application area is seasonal to subseasonal prediction. And here we have a graphic showing what's important to predicting very large rainfall events, if you've heard of those atmospheric river events, over North America 18 days later. And you'll note, if you look at that graphic carefully, that's definitely not North America, because you're looking 18 days in advance. So what matters there, this is a heat map, are things that are happening in Asia. The final application area is coastal oceanography. Here we have a variety of applications. So I have a whole lot of pictures on this page looking at something that is called ocean eddies. Ocean eddies are very large scale circulations in the Gulf of Mexico. They last for months. They have a significant impact on the oil fields that are in the Gulf of Mexico, as well as the traffic. We want to be able to predict both their creation and their dissipation. Looking at harmful algal blooms, predicting how they spread. Looking at flooding, compound flooding from both the ocean and the river, from storm surge. Looking at coastal fog, and then I mentioned the sea turtles. So when it gets really, really cold, like it did this February in Texas, the sea turtles get what they call stunned. They rise up to the surface of the water, and then the ships run over them and kill them. And that's never a good plan. So if we can use AI to improve those predictions, and we actually have such a system in place, it's been in place through our partners for years, we're working to improve it, then we can stop the traffic and the sea turtles can be saved. So this is my super brief overview because I want to be able to get to the other part of the talk, but I'm happy to take questions on these things as well, I will say. It is not enough to develop the trustworthy AI that focus on those foundational methods and then focus on the application areas and then just call it trustworthy. The key to what we're doing is that we have social scientists, and specifically scientists who are trained in risk communication, who are working with our end users and who are studying what it means to be trustworthy, why the end users might trust our science and why the end users might not trust our AI, and what we can do to improve it. So we see that as a cycle, so that whatever they're doing, we can use the information that they identify to improve the AI itself. So their goals are that they want to increase the knowledge and understanding of how transparency, explanatory AI, XAI, reproducibility, and representation of uncertainty influence trust, develop models to understand how attitudes and perception of AI influence trust, and then develop methods to inform the development of the trustworthy AI approaches so that we can use their feedback to directly improve our methods. And to look at what we're doing with the risk communication researchers, we have a variety of hazard use cases. So we just have some pictures shown here. We're starting with the convective weather and the winter weather. And we're interviewing, they're doing controlled experiments, both formative and evaluative research on a variety of different end users, all looking at scientific end users right now. We're not looking at the general public yet, but looking at forecasters and emergency managers. It's late. My words are running together. I shall talk slightly more slowly. Emergency managers, mostly government end users with some private industry end users. Right now, we're starting like as in a week or two ago. We've spent a lot of the first year just getting the Institute off the ground, hiring people, and they worked hard on getting the interview protocol created. And they just started the interviews about 2 weeks ago. So they're doing the pre-tests on the interviews and then finishing the interview protocol, and then they'll be starting the interviews. And these will all be for the convective weather use cases. And then we'll be moving to some of the other use cases. The fourth aspect of our NSF Institute is that of workforce development and broadening participation. These two goals are intertwined. We couldn't be improving our workforce development without also having a focus on broadening participation, because we believe that it's important for both. So we are working to improve the diversity of the AI workforce as well as the environmental science workforce. We have a AI community college curriculum that I will talk about on the next slide. And we're also developing curriculum for K-20. So for all levels, starting at the middle school and going all the way up through workforce retraining. So just summarizing the community college curriculum, this is one of the first community college AI curriculum approved in the United States. There are a couple of them that all happened simultaneously. They're all starting in the fall of 2021. Ours is the only one that's focused on environmental sciences. But it is at Del Mar College where we're prototyping it. And it is something that they call an occupational skills award. You take 14 hours of classes, and then you can either have that occupational skills award or you can transfer those classes into a four-year college. They work specifically with TAM-UCC. One of the other things that we really like about this curriculum, in addition to everything they're doing to develop it, is that Del Mar College is a Hispanic serving and minority serving institution. And this gives us a chance to ensure that everything we're developing is also helping to broaden the participation and that it's applicable widely. And once we show that it is successful at Del Mar, we're going to take it nationwide. So that's the first half. And I knew that wasn't really going to be a half. I knew it was more like a third. Looking at the needs of Fragile Earth and what you all focus on, I wanted to spend a fair amount of time focusing on the need for ethical and responsible AI, specifically for sustainability and for weather and climate. And this is joint work with Emma Eberdupoff, Ann Bostrom, and David John Gagne. They're all parts of AI2ES, they're all members of AI2ES. This is really new work that we just started in the last few months, but it's something we see as critically important. If we're going to create AI in this new sphere, applying it to a variety of weather and climate applications, we really need to make sure that we're doing it in an ethical and responsible way. And as we started down this path, we were thinking, when we first started down this path, we thought, well, there must be other people doing this. As it turns out, there's not. There are other people working on ethical and trustworthy AI, but not for the weather or the climate applications. And we looked at ourselves and we said, well, we are the NSF AI Institute for Research on Trustworthy AI, weather, climate, and coastal oceanography. And if we don't address responsible use of AI for the environmental science community, who will? So we're borrowing a quote from one of the climate summits from Yeb Sanyo of, if not us, then who? And if not now, then when? And this is an important speech. There's a 2-minute excerpt linked in here. it's sad to me that he was asking to do all these things in 2012 and it is 2021 and we have not necessarily followed all the instructions that need to happen. But we are, for us, not necessarily talking about the climate action. For this, I'm just going to talk about the need for the ethical and responsible AI, and AI for sustainability as well. But we really need to make sure that this is happening now, because as the AI use is growing and exploding really across environmental sciences, across weather and across climate, we need to make sure that AI is developed ethically and responsibly, because there are so many ways in which it could go wrong. And we don't need to be in the news 10 years from now, 5 years from now, saying all the things that happened that went wrong. So let's talk about that, and specifically with respect to the needs of the fragile Earth community. AI can help tremendously with environmental justice. Climate change is adversely affecting a lot of the disadvantaged communities. The weather extremes that we're seeing this summer, it feels like it's nonstop in the news, including heat waves. I know there's one going on right now, flooding, fires. There's fires that are ongoing right now, drought, severe storms. It's kind of a non-ending cycle. These weather extremes adversely affect the disadvantaged communities. And if we can use AI to improve our predictions, we can help the disadvantaged communities. That's the environmental justice aspect. AI has already been shown to improve prediction for many high impact phenomena. We need to make sure that it works for all communities. Another way in which AI can help with environmental justice is that AI can be used to simulate sensors. So I had an example of that a couple of slides ago where I used radar on this slide, but for example, if you have one satellite that only has coverage every, twice a day, and you have another satellite that only has coverage every hour, if you can use that twice a day satellite to mimic the coverage that's coming in every hour, and you could get more information more quickly, you can improve your predictions. And these can be used to improve predictions in traditionally underserved places. So I was looking at Fragile Earth's goals and making sure that I'm not just talking about environmental justice, which I know are part of your goals, but also looking at sustainability, because we care about sustainability, although I didn't talk about it in our overview of our institute. But AI predictions can be used to improve efficiency for wind and solar farms, for example. You could improve the efficiency directly of the wind and solar farms by predicting where the sun is going to be highest, whether the cloudiness is going to be, what the wind will be. You want to turn your turbines off if the wind gets too high, if severe storms are coming through. You could also use it to protect your solar farms. I had a fabulous picture. I grabbed this one because I thought it was cute, but we were in Boulder a couple of weeks ago and had an in-person experience of seeing a solar farm that had been hit by a hailstorm. If you could protect your solar panels from the hailstorms, you could save a lot of money and still have your green energy available. AI climate predictions can also assist with choosing locations for new green energy projects, to find the best place to put it, find the best place to put your wind farm, your new solar energy farm, facilitate climate migration, which is becoming more and more urgent need, and just improve resiliency overall. I think probably all of those things are probably somewhat preaching to the choir for this audience. However, let's think about the ways in which we might get it wrong. This is why I wanted to talk about the need for ethical and responsible AI to create this sustainable approach. AI is already used in society everywhere, way more places than people outside of computer science really realize. I think this is mostly a computer science audience, that you probably know all the ways in which AI is being used, but maybe even you don't think about all the times that there's an automated system behind the scenes. I grabbed this picture because it was disturbing and made its way through Twitter a couple months ago. This is a picture on the left of President Obama run through a neural network that's supposed to take some downsampled images and turn them into nice upsampled high resolution images. You take President Obama, you put it through this network, and you get a white guy out. You don't get President Obama out. And it turns out that if you do this to every single picture, whether they're Black or they're Asian, they come out white. And this is an unintentional bias. And you might think, well, all of this stuff doesn't apply to weather and climate, but it does. Because these biases may or may not have been intentional. I don't know that the authors grabbed all these databases of pictures and ever looked through them to see that they were all white people, but they still created bias. And if we do the same thing without looking at our weather and our climate data, and we don't understand that there's bias in our data, we could include perpetuating environmental justice issues. So what I want to talk about for this part is how AI could go wrong for the environmental scientists. And then at the end, what we can do to improve that, make sure that we don't go wrong. The 5 bolded things are the things I'm going to talk about based on the amount of time I have. I may have talked too fast already. We're going to see. I hope I get through all 5 of those. I have 3 more that are on the list that I don't have time to talk about, but I'll be glad to answer any questions. We'll see if we can do this quickly. The first one is model training choices. And so here it really is just a story of, if you have computer scientists who are studying environmental science problems, weather and climate, and they're not working hand in hand with the domain scientists, they may not be choosing the correct model, and they may not be choosing excellent attributes that represent the domain very well. And so they can be making choices that unintentionally bias the problem, or, for example, choosing a ground truth data set that they think is ground truth, but in fact has a tremendous number of biases in it, and they don't know that. I think a more obvious problem, maybe not more obvious, another problem that exists in environmental science is that much of the training data is not representative. So many of the events that we care about predicting are rare events. Tornadoes, I grabbed a picture of tornadoes. Turbulence, aircraft turbulence. It's a project I worked on forever ago. If you think about it, if you're really good at predicting aircraft turbulence and you're getting your measurements from the planes themselves, because you don't have sensors out there that are measuring turbulence across the full 3D volume of the atmosphere, well, your pilots are going to avoid the turbulence. And so you're getting fewer and fewer measurements of turbulence. And over a volume, it's probably 0.0001% of turbulence. And now you think your model's doing great. But in fact, what's happening is just you're getting your pilots are actually avoiding the turbulence. And so you need to be able to create models that actually correctly predict it. And don't just predict no turbulence all the time, because if you get it wrong, just like with a no tornado all the time, when you're wrong, you're really, really wrong. And there's a high impact of that. Another impact in environmental science, there are a lot of sensors out there, especially in the United States, but they are not uniform at all. Urban areas, for example, have far fewer sensors. If you want to study air pollution, it's higher in the urban areas, and yet there are fewer sensors. We have the urban heat islands, but there are fewer temperature sensors in the urban areas. Another one, many of the sensors globally are from the satellites, and they're using visible light. So phenomena are not well represented at night. And one of these, I gave a similar talk earlier actually last week, and one of the people pointed out that more tropical cyclones initiate during the daylight. And the reason they initiate then is that the forecasters are waiting until they see the visible light spectrum before they declare that it's a tropical cyclone. So if you're using machine learning and you're training from all this data and you don't understand the biases in your data, you're training from underrepresented data, and you can create unintentional biases and unintentional environmental injustice. And if you yet don't believe, you still think, well, weather affects everybody equally. Okay, let's talk about the weather that's reported by humans. It turns out the humans are creating biases without really trying. For example, looking at hail reports. If you look at that upper left panel, all the hail reports from 1955 to 2014, what do you see? It's hailing along cities and roads. Well, do you think that actually hails only in cities and roads? Probably not. Probably the hail is fairly uniform. But the problem is that's where the humans are reporting it. So if you don't take this into account, your model could unintentionally create biases. Tornado reports look fairly similar. Don't have time to dive into that graph. This one is a completely fascinating graph. It's particularly along the lines of environmental justice. This is a graph that showed up on Twitter from Jack Sillen. It is a graph of so if you're not familiar with the National Weather Service radar network, there's a nationwide network of the Doppler weather radars. They're placed strategically. When the National Weather Service placed them, they can't see everything. They can only see out to a certain amount of distance because the Earth does actually curve. I know we tend to think it's flat when we're doing a lot of our applications, but it does actually curve. And when Jack plotted this recently, he took the places where the radars could see the tornadoes well. That's the low level coverage, and that's it shown here in green. And then you can see pretty well in the yellow area. It's a little bit upper atmosphere. And he plotted that on top of a map of the counties in the Southeast United States and the percentage of the Black population in those counties. Nobody anywhere is saying that the National Weather Service did this intentionally, but there's definitely a data gap for the counties that have a higher Black population. And the question is, in what way can we use AI to improve the tornado predictions for those areas when there aren't the sensors there? Another set of data bias examples, people, when they do things like predict hail, when they do things like label hail, remember, they label it along roads and cities, but then they also have to say what size it is. Well, they just use common object sizes because that's what they're familiar with. They're not going out there and measuring it because you're getting reports from the general public. And so you end up with non-continuous distributions when in fact hail is relatively continuous. And another fun one, this one is that they stuck a bunch of humans in a wind tunnel, and they said, how well do they perceive the wind speed? They knew exactly what the wind speed was, and they asked them what they thought the wind speed was, and it turns out humans stink at reporting wind speed. Well, and if you think, okay, well, fine, the humans aren't reporting the wind speed. Well, they are. Now, we do have a better sensor network for wind speeds in a variety of locations now, and you compare that on the bottom graph to the wind speeds that are reported for the humans versus the wind speeds that are observed by the sensors, and you can see that the human reported wind speeds are not exactly resembling the observed wind speeds, and they come in 5-mile-an-hour chunks. The fourth aspect of this, so that was one aspect, in that all of that data can be biased and labeled and could really mess with your machine learning models. The fourth aspect, and especially when we talk about robust and creating robust methods, we often talk in computer science about adversaries. And when we talk about adversaries, the first thing you think with weather and climate is there's no adversaries in weather and climate. Well, that's not quite true. Let's talk about the two kinds of adversaries. First of all, there can be human adversaries in the weather and climate data. I just showed you that a bunch of the weather data is created by humans. Humans are labeling the data. They are reporting the hail. They're reporting the tornadoes. Humans can be adversaries. They can do silly things, like is shown here on the right. This is somebody who is hacking into a crowdsourced application called MPING, Meteorological Phenomena Identification Near the Ground. And instead of reporting the weather, they were outlining the state of Alabama. It's not funny, to quote the tweet that's up there. This is not cute or funny. Stop making the work harder for others. People are using this data to do machine learning training, and the weather forecasters are using it to make real reports. And you get stuff like this coming in, especially when there's weather happening. It's adversarial data, and you need to be able to filter it out. And your machine learning models need to be able to filter it out. But even if you realize they fixed this hack that allowed them to hack it, but do you think that stops all human adversarial data? No. Think about insurance fraud. People want to claim insurance fraud.
Can you complete it in 5 minutes?
Yes, I can get there. I'm almost done. If you think about insurance fraud, people report things like 3-inch hail because they want to get a new roof, when in fact they only had 1-inch hail. And yet this data and these reports are used to train these models. Outside of the humans being adversaries, the weather is an adversary. So the weather comes along and it can destroy your sensors. This is a picture of a mesonet station, which is one of the ground stations that records temperature, wind, a variety of sensors. Right after it was hit by a 151-mile-an-hour gust of wind. So they have the recording, and then it destroyed it. Hurricanes, when they come over land, they cut power. So you have all these readings, and then all of a sudden you have nothing. These are adversarial situations, and your machine learning needs to be able to handle it. And yes, I will get done in 5 minutes because we're almost done. This is another part of the environmental justice and sustainability, in that if you've now understood that you might have bias in all of these ways, you need to think about the fact that machine learning can sometimes do things just wrong. It learns things that you didn't intend it to learn. So I have an example. This is brand new, literally hot off the press work of studying a model that was predicting tornadoes, and then randomizing some of the data that's coming in, like literally taking it from the storm structures and randomizing the data across it, and seeing that unintentionally we're still getting high predictions of tornadoes, when in fact these are not physically plausible storms. The machine learning has learned something faulty in this case. And there's some other examples on here, but I won't go into them, just other ways in which we have seen the machine learning learn something that looks like it should be possible, but then it's not necessarily what you had in mind. So I had all of those, I had other ones, but I knew I didn't have time. I wanted to bring us back to, how can we solve this? I just gave you a whole bunch of problems. How do we solve this? How do we get justice and equity, diversity and inclusion and sustainability for use of AI, for the environment, for predictions, for weather, for climate and sustainability? Well, we recruit diverse teams, and I mean diversity in all areas, race, gender, all of that, but also domain scientists, people of all backgrounds, people willing to ask the hard questions of each other. We need to be transparent. The transparency helps with the trust, it helps with reproducibility, and it helps others potentially identify biases, because one of the questions is, the next one, how do you identify the biases in your data? What if you don't know that your data is biased? Well, if you're being transparent in your research, you could have others say, oh, wait a minute, there's a bias in that data, I found it before. XAI and interpretable models can help here. We need to develop novel ways to identify these unknown biases. We need to develop novel ways to communicate uncertainty. We need to ensure our solutions work for all people and focus on environmental justice and sustainability in applications. And finally, because I said I would finish in 5 minutes, this is we are the NSF AI Center for Weather, Climate, and Coastal Oceanography, but long term would like to be studying AI for environmental science more broadly. AI can really help us to be resilient to climate change. As you know, climate change and environmental science are wicked problems. They're deep, they're complex, and we need far more than 5 years of funding to be addressed. We're working on a vision of a multi-agency, multi-sector center that includes, multiple government agencies and funding from all of them, and creating international partnerships. And I'm happy to talk about that more as well. And then there's my NSF acknowledgement for our grant for our NSF AI Center. And that is my last slide. I'm happy to take questions. And since I got out of full screen mode, I can see messages.
Yeah, maybe I will put you on the spotlight now. So
okay.
You will be seeing. Thank you for the excellent talk, Amy. Really appreciate the talk. Maybe I will start with the first question, and in the meantime, the other participants can either put their question in the chat, or you guys can raise your hand so that we can open the mic for you people. Amy, recently in the area of, at least in the NIPS and KDD, we are seeing out of sample generalization or extrapolation based ML models, where you try to understand from where you have collected the data, but applied in a place where you haven't collected the data. Or of course, this is applied on engineering problems like fluid dynamics and other things. Are these kind of models useful for climate and weather scenario, Amy? Have you found success on using this on the real world?
I think they will be. This is one thing we're studying. We're talking, I mean, that the other name of that is transfer learning, right? Transferring from one model to another. Yeah. And we certainly are looking at that. So it's actually useful, particularly for the rare event problems that we were talking about, where you train on one of the, perhaps on something that is similar, but not as rare. So you have more data for it. And then you try to just specialize the model on those rare events.
Thank you. I think Arup, you can ask questions to Amy. Yeah.
Hi, Amy. So I have a few questions, but I'll just ask the first one first, and then we'll see how it goes.
Okay.
So in the climate context, right, there are already approaches, for example, that are based on, there have been statisticians working in climate. There is the whole field of data assimilation, et cetera, as you know very well. So in the context of, as the radiative budgets change, meaning as we go into global warming and some of the relations change, what is your take on why we should be more confident that AI, which sometimes inherently comes across as a little bit more complex than traditional statistical or data assimilation methods, as conditions change, why should AI be the, or one of the tools of choice in climate problems?
I think it's going to give us the ability to adapt, actually. That's an excellent question, right? If we're training now, and in fact, there's a recent paper out from David Gagne, who's part of our AI Center, where they were actually studying the question of whether or not AI would transfer to a warmer climate, and they changed the heat for the severe storms. And they were training the AI method to recognize storms in one environment and then testing to see if it would work in another environment. But I mean, you're asking fundamentally why use the AI there, or why trust it? Why not just use the other methods? I think because it's going to give us the ability to adapt over time gradually. If you train your AI in one regime, as long as that regime is changing gradually, we can keep training it. We can keep adjusting it. And if we've trusted in one regime, we're hopefully going to continue to trust it in the next regime. And maybe not need as many changes.
One question was, see, in climate realm, right? Climate regime, we train based on the recent history, and then we look into the future and sometimes way into the future. So here, whether it's statistics or data assimilation or AI, it stops up to a point. After that, it's projections. But those are, thank you for your points. I think these are larger discussions. It's really, your talk is fascinating and really very interesting and inspiring. So with that, Ramki, please, if there are other questions.
Yeah, Naoki, do you want to open the mic and ask the question to Amy?
I can read it.
Okay.
That's fine.
Yeah, that's fine.
It says, do you have further thoughts on what's unique about the adversarial agents in this climate, I'll say climate and weather domain, as opposed to other domains? That's an interesting question. I would say that the human, okay, yes. The human aspect, I'm not sure they're different because humans are humans, right? The adversaries in more traditional machine learning include things like looking at the speed limit signs and trying to mess with the speed limit recognition, right? I'm not sure the humans have changed. Insurance fraud is kind of the same thing. But the weather providing adversary is very different in that this is the natural environment providing adversaries, and it's really important that you be able to handle those adversaries and maintain your robustness. So the data sets, I think the tropical cyclone was a nice one. This just got pointed out in the talk I gave earlier this week, that if you're looking at a hurricane as it's making landfall and you're trying to make a bunch of predictions, as it makes landfall, it typically knocks the power out everywhere. That's a very large adversary. You now have a whole bunch of data that you don't have measured. And you would like to be able to predict the impacts of this event coming in, and yet you don't have ground truth data because it knocked the power out everywhere. I don't think that that exists in other types of domains. I don't think that nature provides its own adversaries in the other domains. And I agree, I find it interesting as well.
Yeah, so we have another question from Chandrima Amy. Can you briefly mention what are the environmental impacts? Are you integrating to understand causal relationship?
Ooh, I didn't talk about causal learning at all. I don't know if that person wants to clarify so that I know exactly what I'm answering, the causal half or the other environmental science questions. If you're willing to put some clarification in the chat, I will answer. I just don't want to answer the wrong question.
Sure, can you hear me?
Yeah, I hear you.
Yeah, so causal relationship, what I meant to ask was about like you mentioned about the effect to human and effect to environment that is being caused and which you are predicted, and that is what I was interested in understanding, like what's the relationship and what effects are you studying and integrating?
Okay, so I mean, we're studying primarily as a center, we're looking at improving the prediction and understanding of all those weather hazards that I talked about. The studying the human end is largely studying the trustworthy nature. So trying to make sure that the AI we develop is actually trustworthy, and trying to figure out why the humans might trust a method versus not trusting a method and what we can do to improve the methods. Longer scale, I definitely want to look at trying to improve the general public trust, which would be at the larger scale human impact. I hope that answers that.
So Amy, does that mean, oh, sorry, go ahead. Sorry, didn't mean to interrupt.
No, thank you. It's okay.
So Amy, just to sort of follow on that, does that mean, so I mean, I was just recently talking with some folks at the TVA, Tennessee Valley Authority, who use NOAA's operational weather prediction model, the HRRR for example, quantitative precipitation forecast. A lot of that, as you know very well, still uses human input somewhere, right? So there are all these models and things. So is there somewhere where you are saying or where you think AI could make a difference? I mean, one thing is in terms of scaling them, generalizing them. Another is often we find that human inputs, they're incredibly useful, but they are, you know, more, so if I'm a human who is used to the weather of New England, then my insights are more biased there, right? So is that something that AI can help? Sorry, Damki.
I think it can, right? I mean, by recognizing that, knowing that the data that's going in is biased, we can train the models. I didn't have an example in there, but we have recent work showing that we can train a regional hail model to do better than if you try to train a hail model over the entire United States. So the weather forecasters in specific regions learn to be trustworthy because they learn the weather for that region, right? So the AI can be used to improve that. You're asking kind of the other way around, which is also, can we take that data in that might have bias and be able to correct the bias and then create a better model? And I think we can, as long as we know about the bias going into it.
Thank you so much. Ramki?
Yeah, Caleb, this is the last question. Caleb, can you please open the mic and ask question to the keynote speaker?
Yeah, thanks so much for the talk, Amy. I was really interested in how you were talking about the biases that can be present in weather and climate data sets, and then in turn affect models that are trained on the data. With the example that you gave of how that super resolution turned the downscale picture of Obama into some white guy. And that made me think the reason why we're able to identify that particular failure mode of those models is because there's this nice latent variable like skin color that when we visualize, it's readily apparent. Is there something similar that we can look at with weather or climate data specifically, or how can we detect these sorts of problems?
I think it's really going to be an open question to figure out how to detect some of the biases, right? We have to go into, because there might be biases out there that we haven't thought of yet. Like the very hot off the press graphic that I had, we thought that was a great high functioning model, and we were looking at it and we realized that it in fact seems to have learned to filter towards high values of of reflectivity without learning about the structure of the reflectivity. But the only way we found that was to go in and specifically query it for that. And so I think the answer is we don't have a general method to detect such biases yet, but the human has to go in and make sure that what the model has learned looks reasonable, and they have to use a whole, I don't think there's one XAI method out there right now that gives you all of that answers, right? I think you have to go in and you have to query it in a variety of ways. Plot the places where the model succeeds, plot the places where the model fails, figure out why it succeeds and why it fails and what you can do to potentially make it fail. In this case, I mean, we never thought of sending random data in until my postdoc looked at it earlier this week and said, wait a minute, that shouldn't be happening. So I think the answer is just that we need to find a more general way to identify such biases. But right now, query your model in as many ways as you can to see if it's doing something that you don't expect.
Awesome, thanks so much.
Yeah, let's thank the speaker. In the interest of time, Amy, there are other questions in the chat.
Okay.
We'll really appreciate if you can answer them in the chat. Let's thank the speaker by clapping hands on the reaction. That is, if you click on the reactions, you can clap hands. I'm seeing all the participants doing it. Amy, thank you really for taking your time, and appreciate your time on this weekend late in the evening. So for any further questions, please reach out to Amy over email, and let's move on to our next technical session.